All right. Hi, everybody. Thank you all for coming out today. We're Group 19.
My name is Alexis Claudia.
I'm Kyle Carmen.
And I'm Gianni Guido. And today we'll be presenting our project on the 2021 Sunseeker Solar Car Performance Model. Our faculty advisors are Dr. Richard Meyer, Dr. Bradley Design, and our customer is the WMU Sunseeker team. So the first ever solar car was created in 1955 by a General Motors engineer named William Cobb. It was actually a short scale model that they presented at an auto show. So Western Michigan University has a Sunseeker Solar Car team that has been designing, building, and racing solar powered cars since 1990. And to gain a competitive edge in races, they focus on performance modeling. And I forgot to mention that they participate in events such as the World Solar Challenge, the American Solar Challenge, and the Formula Sun Grand Prix to name a few. And these races consist of anything between cross-country racing, where you want to drive the furthest amount of distance, or track racing, where you want to have the best time. And to gain a competitive edge in these races, the team focuses on performance modeling, which involves dynamometer and on-road testing. And these tests provide us insight on important factors that affect the car, such as solar array efficiency, rolling resistance, input power, and aerodynamics. On this slide, you can see the 2021 model solar car that we performed all our testing on, as well as previous models that the team has built in the past, and their platinum sponsors, who spend between $14,000 and $25,000 on the team.
So the problem statement is the Sunseeker team has built a new 2021 model, and there's no data supporting the vehicle's performance on it. And there's no plan to standardize any modeling or testing procedures. Without these modeling and testing procedures, it's unclear how the car will perform in racing. The project goals are to conduct our own testing and modeling and present our findings and techniques as a product to this.
So next we have our project schedule, and on the left shows the different project tasks that we wanted to implement during our past 2 semesters. So last semester we spent a good chunk of our time analyzing the data that we received on the Sunseeker's 2016 model, as well as some of the data that we got on the 2021 model. After that, we met with our faculty advisors and members of the team to go over different testing procedures that we would want to go through with the following semester. Once January approached, we started off by going through our testing procedures and guidelines to perform the dynamometer testing, which is located on Parkview campus. Once we performed the dynamometer testing and obtained all the data that we wanted for performance modeling, we also spent that time creating testing procedures for our on-road testing that included both coast-down testing and track lap testing. Anytime that we had clear weather this March, when it wasn't raining, we performed that on-road testing for both the coast-down testing and the track lap testing. And we have spent the remainder of our time analyzing the data that we obtained from that on-road testing and creating models that would benefit the team for racing. So next we have our energy conservation model. This is a representation of the Sunseeker Solar Car's operation. On the top left-hand corner, you can see that weather, location, and time of day are all inputs that impact the vehicle's solar array. The solar array is used to charge the battery of the vehicle, and the battery is also a source of electric power that can be distributed to both the motor controller and the motor of the vehicle. The motor controller controls any of the electric current flow based on the driver's input. You can see that the energy loss coming from the solar array and battery comes from any of the wiring that connects the battery, motor, and the solar array, and also any connections that charge and operate the vehicle's lighting. On the right-hand side, you can see that road grade, rolling resistance, and any aerodynamic forces are all inputs that impact the vehicle dynamics operation of the vehicle that essentially comes out to be the desired vehicle speed.
So aerodynamic and drag forces, they oppose the motion of the vehicle, and it's important to understand these to get an idea of how they'll affect the performance. The aerodynamic is the force that resists the vehicle's motion through the air. It's a function of the density of the air, the drag coefficient, velocity, and the frontal area. The drag coefficient is dependent on the shape of the vehicle. The rolling resistance is the force that opposes the vehicle's motion due to friction and deflection in the tire on the contact patch where the tire meets the road, and is a function of the coefficient of rolling resistance and the weight.
So the first kind of testing that we did was dynamometer testing. You can think of the dynamometer as a sort of treadmill for the car that allows you to simulate driving on a long, straight, flat road. Because of this, there are some error in the data that we gathered, such as factors like wind resistance, rolling resistance, stuff you can't simulate. And it's important to note that the dynamometer available in Parkview's campus can simulate wind resistance. However, for our testing, we did not utilize that feature. To hook the car up to the dyno, you simply align the back wheels of the car with the wheels of the dyno, and then you can strap it down, as you can see in the pictures of this slide. Testing procedure was co-designed with us and the team, the Sunseeker team, and we'll go into that in the next slide. So a data logger was connected from the motor controller of the car to a computer that could then export an Excel file of information like velocity, power, current, voltage of the battery. And so for our testing, we had a driver start from rust and accelerate up 2.23 meters per second or 5 miles per hour, where he would maintain that velocity for 30 seconds. And once that 30 seconds is up, he would accelerate another 2.23 meters per second or 5 miles per hour. And this was repeated from 0 to 29 meters per second or about 65 miles per hour. You can see that we have a curve of power versus velocity. And as you want to increase your velocity, it obviously requires more power. And then it's important to note the vertical spikes in the graph represent when the driver was maintaining that constant speed. So it's clear to see that it requires less power to maintain speed, a constant speed, than to vary speeds.
So here we've filtered our data into the increasing velocity and the constant velocity, increasing shown in orange, constant shown. And as you can see, holding a constant velocity requires 30 to 40% less power. And it really highlights the importance of reducing your fluctuation velocity to conserve power on these long bases. The dynamometer did not take into consideration the rolling resistance of the front wheels or the aerodynamics. So in order to gain more knowledge and information on that, we'd have to do that.
Yeah, so like Kyle said, secondly, we performed on-road testing of the vehicle, which provided things like rolling resistance and the aerodynamic forces that the dynamometer was not able to provide us. So to start off, our team met with our faculty advisors and the team to implement a testing procedure for coast-down testing that would have a list of set variables and instructions to follow. As you can see, the image on the right-hand side shows the coast-down route that was chosen between us and the team, and this screenshot is from our data logger that we use that also shows the altitude. So first we started off by agreeing on a certain route that we would use for our coast-down testing. And because the vehicle was not running consistently, we decided that staying local around Parkview campus would be the best option to perform this coast-down testing in case the vehicle was not able to run. So to perform this test, once the point was specified on the road to start the coast-down testing, the driver would hit that specific point on the road and release their foot off of the acceleration pedal and coast to a complete stop. So during this whole coast-down testing, the driver had a data logger in the vehicle with them that was tracking the set variables and distance and time and things like that we were looking for to make our models in the end of it. So this data logger had things like time, velocity, and distance traveled that were recorded. So here is a screenshot of our coast-down testing procedure that we created and implemented with the team and faculty advisors that was approved. So By having this, the Sunseeker team can use this towards their current and future models and use for enhanced vehicles. Then lastly, it shows our coast down testing results that we obtained. So we performed 3 different coast down tests. You can see the bottom yellow one had an initial velocity of 6.5 meters per second, or about 15 miles per hour. The middle set of data had an initial velocity of 12.5 meters per second, or about 28 miles per hour. And then the top blue data shows an initial velocity of 16.2 meters per second, or about 36 miles per hour. So after we recorded and plotted all of our 3 different coast down testing, comparing the velocity over time, and created a best fit line for each of those coast downs, we could see that they all had a consistent.
And using the data we gathered from the coast down testing, along with given and measured variables, we were able to solve for our coefficient of rolling resistance. And to do that, we wanted to use one velocity input. So we derived an equation for acceleration in terms of velocity to ensure they had a linear relationship. And we plugged all our values into our force balance and calculated the coefficient of rolling resistance at 5, 10, 15, and 20 meters per second, and came up with a value of 0.03 rolling resistance, with standard deviation of 0.006. And this is a pretty standard number, considering that we didn't account for misalignments. In order to develop this model even further, the team can solve for the propulsion force. The propulsion force is the force that leads to the movement of the vehicle. And when solving at constant velocities, according to the force balance, it becomes the force that's needed to overcome the rolling resistance, drag, and the road grip. Force of propulsion can be solved for various velocities, accelerations, and road grades, and then related to the input power and motor torque output, which kind of ties all this modeling into powertrain efficiency and development.
To further develop our model, some improvements that might want to be made in the future would be for the team to acquire a portable data logger that would hook up to the motor controller of the car. For all of our testing, we used a GPS-style tracker that mounted to the dashboard of the car, which obviously again leads to some inconsistencies in testing. Something else they might want to consider is including wind resistance in their dynamometer testing to give them a more realistic performance of the vehicle on public roads and tracks. Finalize testing procedures further, and this helps by reducing time spent on research, planning, and all that, and now they can archive our procedures and to edit however they see fit for future models. And one other thing that they might want to implement is a cruise control feature. And now cruise control would greatly optimize the car's performance by reducing driver error. And if you recall our dynamometer results slide, it takes much less power to maintain a speed, which is the whole point of cruise control, is maintaining that speed constantly.
So project impact, this project has a huge impact overall on engineering. Sunseeker Solar Car team at Western brings various backgrounds of engineering and business majors together that all have the same purpose of creating a more improved Sunseeker model than the previous year. This also gives students a better insight on vehicle components and different testing guidelines that are used in the automotive industry today. So students can take what they've learned by being part of this team to their jobs or internships, or also take what they've learned from these jobs or internships and back to the Sunseeker team for.
Yeah, and as us as a team, this project was great because we're all automotive focused engineers, and that's what we were planning on pursuing post-graduation. And this project gave us a lot of knowledge on not only solar powered cars, but electric powered cars, which is important because in the current shift of the automotive industry from internal combustion engine vehicles to electrical vehicles, this project is something that we can take beyond the classroom and use in our career down the road. We also obviously enhanced our communication skills and team building skills. We also had experience writing our own procedures and then executing them. So here is the wheel rolling on the dyno wheel. So I just did that for all of its speeds.
Okay, so limitations and recommendations. For future testing, trying to find a more straight path to perform the coast down testing would be ideal and have better data outcomes. Things like potholes and sharp turns were kind of affecting the data that we received, so trying to find a better straight path. And by finding this different location of a straight path, it would better correlate with the dynamometer testing, because that was very common.
And then there are some other limitations we ran into that were out of our control, such as weather. The car is not waterproof, which means that if you take it out on a rainy day, you risk damaging the connections and battery. So the vehicle was not always drive ready, which limited our schedule on testing. And then we also consumed some minor losses because the car's never a proper alignment.
So again, thank you for being here. We'd quickly like to acknowledge our faculty advisors, Dr. Richard Meyer and Dr. Bradley Design, for mentoring us through our project and going over testing procedures and guidelines. Secondly, we'd like to acknowledge WMU Sunseeker team and their president, Joe Malega, for allowing us to test their vehicle and meeting with us over the weekend to perform the coast down testing. And then lastly, we'd like to acknowledge our ME48 course instructor, Dr. Bade Shrezka, on mentoring us these past 2 semesters for our senior design project and showing us. Thank you.
Ideally, it would have.
Okay, but so so you don't consider incline in any of your equations, correct?
For propulsion force, ideally for the coast down, we'd like to have a 0 degree.
The dynamometer has capability to
It did.
dynamometer. I don't know.
Yeah, the new dynamometer creates a moment on simulating different resistances. That's in our future recommendations.
The mileage, 5 hours. Sunseeker.
Oh,
Oh,
that's
what
the-
are
And how fast?
on the dyno, we got it up to about 65 miles per hour.
65.
Yeah, we were.
Yeah. And then when we were taking it around Parkview, we got up to 45 on the road. So, yeah. And then we just had to watch out for potholes because a couple times we did hit a bump and then it was a connection and stopped the car.
What is the efficiency? Someone.
Off the top of my head, I'm not sure because all of our testing did include the solar, but not exclude
Solar cell.
yeah, I'm not sure because the solar array was not on the car, correct?
20, 25. Because I don't know.
Yeah, off the top of my head, I'm not sure.
Excuse me. So in several instances, there was a claim that fueling resistance was not part of the dyno testing. Okay. So how did you come to that conclusion? Fueling resistance is really about tire deformation.
Yeah, so I mentioned that the front tire rolling resistance was not testing. So the wheel was only contacting the rear wheel. Rolling resistance is dependent on the contact batch, which is the area of the tire flat road surface. Because the dynamometer didn't have that flat surface, it had more curvature, it was an accurate representation.
But even though it's a curved cylinder, it's a much smaller radius than typical pavement radius, because we could look at pavement radius is nearly infinite. Well, curvature of the earth. But very large compared to the dyno.
Yeah.
So there's still going to be some tire deformation, even if you're on that smaller radius cylinder.
Yeah, I agree.
Just instead of, it's more of a cup.
Yeah.
Flat surface.
Just doesn't accurately affect what toe would have.
Well,
So
you,
it is.
when you were testing, okay. So when you were testing on the dyno, right, you had power requirements.
Yeah.
Right. But I don't believe you had a granular enough knowledge of all the power distributions to know whether or not rolling resistance was actually what was happening with rolling resistance. But I don't believe you did a complete energy breakdown. Just looking at basically sort of a more global view of what was occurring, because that power is just power from the battery, right? Yeah. So that power could have been consumed by a small amount by the rolling resistance. There's also electrical losses. There's internal battery losses. There's motor efficiency losses. But you never had that granularity. So I would caution you to not claim that there was no rolling resistance. Or you could say that we didn't break out our energies into that fine granularity, and that's fine. And the claim that you didn't have aerodynamic drag is perfectly fine. Okay. But just be careful.
Got it. Thank you.
I guess I have one. I would have to assume that the solar car has a set of qualities they, designed for, like coefficient of drag, rolling resistance, stuff like that. And I was just curious if you guys knew what those were, and if so, how closely those correlated to what you guys found in your testing.
Coefficient of drag's 0.23.
That's what they designed for.
Yeah.
Okay, so wait, 0.23 or 0.023?
2.3 for the coefficient of drag. The coefficient of rolling resistance was 0.03,
Okay.
which is pretty standard for tires on asphalt.
Okay.
So, that like you would try to implement a power low because if it's going at specific velocity, or you have to like account for different like gradients too as well. Wouldn't that affect the power if it's going?
Yeah.
So, how do you implement that in cruise control?
We didn't design any cruise control.
Yeah.
Cruise control just get closed feedback loop, depending on what it needs to overcome.
You show on the slide with your calculation of propulsive power. And
Yes, I think cruise control would take into consideration what the force of propulsion needs to be to overcome, including the.
I know that like the FSA teams have this like a formula for what they're allowed to change and those things that is there something similar for the Sunseeker team, where it's this more open and implement different things like what a cruise control be allowed in.
Yeah. So they have specifications on weight, size of the car, wheel diameter, and that kind of stuff. Which off the top of my head, I'm sorry, I don't know. But
I know
yeah. But as in terms of like what functions the car has to drive, yeah, cruise control's totally. Yeah. So here's the filters data.
Yeah. Other constant. Yeah. The other one. The one is the acceleration, right?
Well, one is increasing velocity.
Increasing velocity, so accelerate.
Yeah, so this is over the period of the whole testing.
Yeah. The other one is the constant.
Yeah. So it is a graph of velocity. So we didn't want to call it acceleration, but
So mostly the drag force constant.
No, it's a function of the velocity squared. As velocity goes up, the increases.
Check with your cars.